Okay. It's my great pleasure to be here at this conference and this beautiful place. I would like to thank Paul and other organizers of this conference for inviting me. This is a report on a paper we posted on March, first day of March, on quantum supremacy. But before getting to the details of the paper, I want to start by giving you a brief history. This is a conference on quantum annealing. So annealing is the main subject. Annealing was first proposed back in early 80s by Kirkpatrick. This is a seminal paper published in Science in which simulated annealing was proposed as a way of optimizing NP-hard problems. It took 2 decades until people started thinking about quantum version of that. Of course, we are all familiar with the Kadowaki Nishimuri's seminal paper, which introduced the quantum annealing. And okay, that's good. A bit later, people started trying experiments to verify that quantum annealing is better than classical, which was proposed in Nishimuri and Kadowaki's paper. And this is the first, or maybe the only experimental trial published again in Science in 1999. At that time, there were no quantum annealers, so the only thing that you have access to was materials to do the physics of quantum annealing. And we know it's impossible to simulate large problems quantum mechanically. So this is a paper by Gabe Apley, Tom Rosenbaum, and others. What they did, they looked at a disordered magnetic material, more specifically a lithium holmium compound, which became a spin glass at low temperatures. They cooled it. They annealed. By annealing, we mean you gradually cool it down or make quantum fluctuations go down slowly, so that the system settles at low energy states. So I'm hoping people in this conference know this term annealing. So what this paper did, they cooled down this material thermally towards within a spin glass phase. They also annealed it quantum mechanically at low temperatures. And the way they do it, because it's material, if you apply a magnetic field in the perpendicular direction towards the icing direction, it behaves like transverse field. It is a transverse field indeed for the spins. And so if you bring it down from large magnetic field to small magnetic field, this basically effectively quantum annealing. And what they concluded was that doesn't work. Quantum annealing converges faster to optimal solutions than classical. Of course, the conclusion was not reached directly, because you cannot measure the spins in the material and find the energy. So it was an indirect conclusion. I'm still not confused about how the conclusion was made. But nevertheless, that was a very important milestone in quantum field of quantum annealing. Just for your entertainment, this paper was published in April 1999, the same year and month that D-Wave was incorporated. For your entertainment, this is the first check, the first investment in D-Wave made to Jordi Rose, the founder. And I want to look at the amount. It is $4,000. And also, 1 year later, this is at the conference in Utrecht, Netherlands. Me and my colleague Tim Duty sitting down with Gabe Apley at dinner. probably talking about how cool it would be if one day somebody could do this experiment by a quantum annealing machine, which at that time was completely impossible. Sounded impossible because the state of the art was 1 qubit with sub-nanosecond coherence time done indeed in Japan by Nakamura et al. And this is an updated version of the picture taken last week in Houston. Okay, so people have started thinking about how to understand or theoretically understanding why quantum annealing could be faster than classical. And one of the papers was again published in Science 2002, 2 years later, or 3 years later. And this is a paper by Santoro et al. Again, there was no way to simulate quantum annealing because otherwise we didn't know quantum computers. So they used quantum Monte Carlo as a proxy for quantum annealing. What they found was in this picture, summarized in this picture, the y-axis is the residual energy, which means that the distance between the optimal solution. So the objective is to reduce the energy of a problem. In this case, is again a spin glass. And the closer, the lower the energy, the residual energy, the better. So they find that as a function of time, which is x-axis, and for this problem, these are 2 algorithms, simulated annealing and quantum Monte Carlo. And the x-axis is the number of sweeps you do in the algorithms. And they find that the quantum Monte Carlo scales better, which means converges with higher slope towards the grounded state than simulated annealing. This laser doesn't work well. And this little difference was enough to make this paper published in Science. So there's a evidence that something quantum mechanical, although quantum Monte Carlo is not simulation of quantum annealing, something quantum mechanical can bring some speed up. But the problem is, as I just said, quantum Monte Carlo is not simulation of, it's just an algorithm. It's not simulation of quantum annealing. So still the question remains, if you have a quantum annealing, where would the real quantum annealing land on this plot? And it took another 2 decades and many generations of our hardware development until we had a large enough and coherent enough quantum annealer to answer this question. I'm putting this is a paper, in a picture, a figure from a paper we published last year in Nature. And so now you see, this is again 3D spin glass, the same problem as Apley et al. Studied in real materials. Now we're doing it in a quantum annealer. So the dream came true, which I talked about. So now we see that quantum Monte Carlo and simultaneous annealing behave very similar to what Santoro et al. Predicted or computed, which we recompute. But D-wave scales better than both quantum Monte Carlo and simultaneous annealing. But what is more significant about this result is this is not just empirical. This is not just a result coming out of experiment. You could actually explain it theoretically. And these lines are both blue and green and orange are predictions coming out of scaling theory, quantum critical phenomena. So it turns out that with quantum critical phenomena, you can predict this kind of a slope. And indeed, quantum annealing should be faster than classical. I'm very surprised. Nobody did this before our paper. And we collaborated with Anders Sandvik, one of the experts in this field, and he derived the equation necessary to make this prediction. Ooh. It is shared.
is shared. In that case, we have a problem elsewhere, but carry on. Thank you.
Okay.
Sorry to interrupt.
All right. The problem with being the first speaker is all the technical problems, you and the rest of the speakers are fine. So I'm happy about that. Anyway, so the very important point about this work is actually, as I said, it's not just experimental. You could actually theoretically predict that quantum annealing converges faster than classical based on a scaling theory. But what is even more significant about these results is this is a simulation of quantum mechanics at 5,000. This is done with 5,000 qubits. This is simulation of quantum mechanics at the level of 5,000 qubits, and there is no way that anybody can simulate Schrodinger equation at 5,000 qubits. And indeed, one of the referees of our paper in Nature asked this question: is this supremacy? Which we were actually thinking about it before the referee asks. However, it is not easy to just claim supremacy. And we have seen that many people did, and they failed. And the reason is, if you want to show supremacy, you have to prove two things, or you have to answer two very important questions. One of them is your QPU should have low error. If your QPU returns answers with big error, there is a way to simulate it with the level of the error that your QPU I mean quantum processor unit. I will use this. I hope it's a quantum analog of CPU. But the second question, which is even more important, and it was ignored until recently, is, are quantum correlations long-ranged? And this is where all previous supremacy demonstrations failed. Because when the quantum correlations are short-range, there are techniques that can leverage short-range correlations and simulate the dynamics, which happen to a lot of other teams, including IBM. And indeed, I think this week, Google published a paper in Nature showing, I think, the first supremacy in gate model, which was not refuted. And the whole point of the paper is exactly that the correlations are large enough that if you want to simulate with the level of the error, you have to simulate a lot of qubits, and that becomes exponentially expensive. So what I want to do for the rest of this presentation to convince you that these two is satisfied with our supremacy demonstration. Okay, this is the paper. If you haven't seen it, this is the archive. It is collaboration among 11 institutions, many experts in the world. Especially, I want to acknowledge Andrew King, who did lots of experiments and the hardest work in this work, and Alberto Nocera from UBC helped us with MPS, tensor network simulations. Marek Rams and Jacek Giormaga, they did PEPs. I will talk about both of them. And all colleagues at D-Wave, which did a lot of work. This work was not possible without collaboration of all of them. So, okay, so what do we do? We define a problem. So this is, again, another difference between what we do and the previous supremacy demonstration. We define a problem that's interesting, physics interesting. It's not just random number generation. It's not, and the problem is not the hardware, is a problem defined independent of the hardware. And the hardware has to try to solve the problem. Whereas in other demonstrations, oh, this is the connectivity of the circuit, the chip that we have, and let's see what we can do, and then show that classical cannot do. This is different. So we define problems which are interesting, independent of the hardware. We program the QPUs to solve that problem, and we program two QPUs with two different topologies, different connectivities, different fabrication layer, different even qubit design to solve exactly the same problem. So we don't adjust problem to the QPU, we adjust QPU to the problem. So the problem we solve is quenching a system through a spin glass quantum phase transition. So what it means is we have a Hamiltonian, which is the classic quantum annealing Hamiltonian that has a transverse field which anneals towards zero, and a problem Hamiltonian, which in this case is a spin glass Hamiltonian. And we change these coefficients of these two Hamiltonians in this particular way. And this particular way is shared between two processors, which are very different, as I said. And these JIJs are programmed to topologies of a square lattice, cubic lattice, diamond lattice, and bi-clique problems, which are very popular for RBMs. So these are very interesting problems. These are problems relevant for material science. And so we quench through. Once you quench through this, change this gamma and j according to this schedule, gamma from large to zero and j from zero to a large value, the system passes through a phase transition, quantum phase transition. And because of that, you can observe critical quantum dynamics. And so our goal is to simulate that by 4 means. One is, of course, the QPU. It's a quantum simulator. That's the purpose of this experiment. But then we want to do it classically. And classically, there are 2 state-of-the-art techniques that exist right now. One of them are tensor networks. The other one is neural networks. And tensor networks, again, the best tensor network techniques are 2 called MPS, matrix product estates, and PEPS. And we study both of them. And we study neural networks. And we compare the results. And the idea, the goal is not to demand this classical simulator to solve the Schrodinger problem exactly. We demand the classical solver to solve Schrodinger equation with the same accuracy as D-Wave. So the demand is we want to reproduce the same accuracy, the same error level as the QPU generates. Okay. For computational resources, we use D-Wave advantage. And for classical computation, I tell you, this is a heavy, very, very, very heavy classical computation to do this work. And it was not possible to do it by our laptop or even our clusters or anything. So we really needed supercomputers. And Oak Ridge National Lab was nice enough to give us access to 2 of their high-end supercomputers, Summit and Frontier. And Frontier is now considered as the fast or one of the fastest supercomputers in the world. So we are basically comparing results with head-to-head with the fastest supercomputer in the world. Okay, so now let's move on to the experiment. So the first thing, as I said, I want to show you is the error level of the QPU is low. And by low, it means it still is classically hard to simulate to the error level that the QPU generates. So let's start with a small problem. We first consider a 6x6 2D lattice on a cylinder. This is the topology. And we run QPU and run simulator. So before I move on, I want to tell you, among all these classical techniques that I told you, neural network and tensor network did not work. So I'm not going to talk about neural network at all. And tensor network are 2 techniques, PEPS and MPS. MPS works better, and MPS has this advantage that there is one parameter called bond dimension, which I'm going to mention a lot. And if you guys don't know tensor network, it's okay. There's one parameter that if you increase, the number of parameters in your representation becomes larger and larger and larger until it becomes exact. So there's one parameter which controllably you can reduce the error or increase the accuracy like tune a knob that we can tune the accuracy until it gets exact. So, and the idea is when you don't need to get exact, as long as all the quantities that you care about saturate, then we say this is the ground truth. So when I say ground truth, means not exact, but at the point that all the quantities that we care about or we show saturate. Okay, so now let's just start with 6 basics problem. It's an easy problem for MPS. And we solve this. It's a one instant of random instant spin glass problem. We run QPU, we run MPS. We take samples. We generate some quantities. It doesn't matter. One of them is called a spin glass order parameter. It's a sum of correlations. It's okay. And the other one is residual energy, which I talked about previously. And in this plot, the symbols are the outcome of the QPU after sampling and averaging. And the orange is the exact, or not exact solution, the ground truth coming out of MPS. And you can see they agree very well over 3 decades of annealing times. The x-axis is the annealing time. And I want to emphasize there is no free parameters. We did not fit anything. We just calibrated the QPU, measured all the quantities that we entered the Hamiltonian, solved the Schrodinger equation, and this is the level of agreement we get. So visually, it is very, very appealing that this machine is doing great. But you have to make it quantitative. So the error should be quantitative. And so let's look at another quantity. So let's look at all the correlations one by one. So maybe those 2 quantities were averages. Maybe correlations don't agree, but on average they do agree. So this is correlations generated by the QPU, and these are correlations on the x-axis, the ground truth correlations. And you see when it's on the 45-degree line, that means they agree completely. So you see they're very close on the diagonal line. Therefore, the agreement for all correlations that generated are very good between every pair of qubits. And so whenever I showed tilde, it's your ground truth. We also do look at all the probabilities, and we see even all the probabilities, they agree pretty well with a small error. Okay, so with correlations, we can define now error. So the error we define for the rest of the presentation is the distance between the correlation between every pair of qubits and the ground truth. Normalized, and this is some quantity between 0 and 1. So I don't want to talk about fidelity. The fidelity is not scalable. I don't want to waste time. So now, if I reduce the bound dimension, I said in MPS has one tuning knob, which is called bound dimension. If I increase it, becomes exact. If I decrease it, becomes approximate. So I can actually tune this knob until the result generated by MPS looks like what D-Wave does. And this is what we do here. And we see that although the ground truth was 256, at much smaller chi, the data looks very similar to what D-Wave does. The error level is the same as D-Wave, both for correlations and even the probabilities. So even probabilities look very the same. And then we say that, okay, this level of approximation that we use for MPS is equivalent to the level of the hardware error. And we can even quantify it using this error, epsilon c, or correlation error. And we see that basically the errors look the same. Both of them are like 0.6 to 0.8. So this is this chi-q, which is 65. We call it QPU equivalent bond dimension, which means the level of approximation you need for MPS to generate something equivalent to Q, looks equivalent to the QPU. Okay, now let's move forward. So this was just one problem, one instance of one problem. Now we want to see for many problems and many sizes how this error scale. And this is what this plot shows. And indeed, the error does not scale. As the problem becomes bigger and bigger, the error stays almost constant. And more importantly, the two QPUs, which were very different, as I said, to solve the same problem, actually show very similar results. So they're doing the same almost. Okay, now for every size, so this is different sizes from, I think, from 4 to 8, 4, 5, 6, 7, 8. For every size, we can actually change this knob of MPS, the chi, the bond dimension of MPS, until the MPS reaches the level of error of QPU. So for L equals 4, it is here, and then for L equals 8, it is here. And these are chi Qs that we care about. So these are the level of error required to reach the same level of error that QPU generates. And these numbers are very important. So we plot them as a function of L. And L is a linear dimension. It's not the number of qubits. So if it's 4, it means 4 by 4, 16 qubits, or 8 is 8 by 8, 36 qubits. Sorry, 36 qubits. And so now what we observe is when you plot chi q as a function of L, it is linear. For all problems, all sizes, it is linear. And this is expected based on a very important law of physics called the area law of entanglement. Area law of entanglement, what it is, again, for many of you, you may not have heard of it. If you divide a system into two pieces and say how much one side is entangled with the other side and find entanglement entropy, what happens is this entropy does not scale with the volume. So we can actually increase the number of qubits on each side. As long as the area does not change, the entanglement entropy does not change for the ground state. So this is the ground equivalent for the ground state. And so, but if you change the area between the two sides, the entanglement grows. And the entanglement is, the chi q is exponential to the entanglement entropy. Therefore, linear means exponential, and it is in agreement with area law of entanglement. This is very important because we're going to use it for extrapolation. Okay, so what this tells you is now the error, because we calculate this chi q to the level of the error. This tells you that the error the QPU generates is low enough to demand exponential growth of resources, because chi q is exponential and follows area law of entanglement. So this at least for this class of problem, which is 2D lattice, which we don't use it for supremacy, I have demonstrated that the QPU error is low enough to demand exponential resources. But I still have to answer the next question. And this is a little bit more delicate. How much time do I have? Do you know? Okay, so I have time to go to more detail. This is more delicate. So when, as I said, when the correlations, quantum correlations are short-ranged, there's a technique that you can actually leverage that, and it is scalable. And that technique is called tensor contraction, or in some other called PEPS. And so in order to demonstrate that the correlations are long range, we use PEPS. So if PEPS can simulate, we did all the techniques that we can. If PEPS can simulate, therefore, it is short range. If PEPS cannot simulate, then there's a chance that it's long range. So let's go over PEPS. This is a little bit technical. If you don't know tensor network, just listen to the high level. You don't need to know anything very detailed. So tensor network is basically you represent the wave function as multiplication of tensors. And these are tensors, and every bound is basically one index of tensor that you sum over. This is not very important. What's important is every tensor that represents in PEPS represent one qubit, and the connectivity is the same as the graph that you are simulating. So that's the very important aspect of PEPS. The way PEPS works is very similar to gate model. If you want to simulate Schrodinger equation, you divide Schrodinger equation into very small steps, and then you trotterize again. If you don't know, you basically divide it into 2-qubit gates with some approximation. So 2-qubit, 1-qubit gates, and then you apply all of them one by one. And very similar to gate model. That's why for gate model, they even don't call it PEPS. They just put the network, the circuit in this representation, and they just contract it. But for us, we don't have gate model. We can actually artificially define gates. So the way it works is you define your continuous time Schrodinger equation into a small, tiny gates. So let me apply one gate, which represents a tiny bit of evolution, which basically applies the coupling between these 2 qubits. As soon as I add a tensor to this tensor network, the number of parameters grow. And if I keep doing it, the number of parameters explode. So there is a technique to make it back to the same size so that the parameters does not grow. So in every step, the parameters grow, and you bring it back. So the way you bring it back is you combine this tensor to a bigger tensor, you shrink it down, and this is the problem. When you shrink down the dimension, the bound dimension, the number of possibilities of this index, you want to shrink, you want to contract this bound, but it screws up all the qubits in the neighborhood. So that's the problem. That's the problem that you need short-range correlation. So you want to do one gate, it screws up everything. The other gate, it screws up everything. If the quantum correlations are short range, this region that I made pink is small and you can handle. As the correlations become bigger and bigger, this region becomes bigger and bigger. You have to handle the whole thing together. So this is called neighborhood update. So you have to apply this neighborhood update to a large number of qubits. This is a very expensive computationally. And so our collaborators, Marek Rams and Jacek Giermaga, who actually one of the inventors of this technique, and they're the world's expert, they tried all sorts of neighborhoods to basically there was a fight for them to just simulate, and for us to, oh, you cannot simulate. So it was kind of for them to try hard to simulate what this machine does. And they tried all sorts of neighborhoods. Some of them are very large, but approximate. Some of them are exact and small. And it turned out that the best neighborhood that worked for the 2D lattice that I showed you previously, the 2D lattice, L by L. I'm just showing you the 8 by 8. The best neighborhood that could simulate that was this type of neighborhood. Don't worry about the title, Plaquette nearest neighborhood plus. So they invented this name. But the most important thing is every tensor does not represent 1 qubit. Every tensor represents 4 qubits. So you can just calculate in your head how many qubits this neighborhood is. It's a huge neighborhood. And so with this neighborhood, they were hoping that they can simulate. And they indeed could simulate when the annealing time was short, and the PEPs beat it, QPU, because when the annealing time is short, correlations are short range. When the annealing time is 7 nanoseconds, then basically they could not beat at a small bond dimension, but if they increase the bond dimension is again the same one knob that you can change to increase the number of parameters in your representation. And as you increase the bond dimension, basically the error went down, and again they beat QPU. But when you go to 20 nanoseconds, you see that it saturates. And what saturation means is that the more you increase the number of parameters in your wave function, and you're hoping that if it becomes exponentially large, you can solve the problem, but you can't. And the reason you can't is the neighborhood is so large that every time step, tiny time step, you have to consider the whole qubits, and that becomes exponentially difficult. So therefore, if they want to increase their neighborhood one step further, it becomes the whole 60 for qubits. So so we call it system spanning correlation. The quantum correlation span the whole system. The only way to simulate is basically to simulate all the qubits, not just sub systems or smaller subsets of the qubits. Okay, so with that, then we go to the larger number of the higher dimension than for two dimension. I mentioned we don't claim supremacy for two dimension. Two dimension is easy eventually. There are ways to simulate. For other problems, which is cubic lattice, diamond lattice, and biclique, again, we calculate, so we do the same, follow the same protocol. We calculate error as a function of size, and we see that the error remains flat, except for biclique. But you see the difference between from 2% to 3%. Still, we consider it a small change from 2% to 3%. And even this change is considered in the calculation of the chi-q, the QP equivalent bond dimension. So for all of this, all of these pink symbols are calculated, the bond dimension, the resources required to reach this error, and it is already considered this dependence, size dependence. And once again, we see that the QPU resources, chi-q, or the number of parameters needed to simulate to the level of approximation that the QPU generates, a scale exponentially, but now exponentially, not with L, exponentially with area. So we plot as a function of area, and by area we mean n to the power of d minus 1 divided by d for every d, for fd is a dimension. And for all of the cases, again, we get linear dependence. Again, it follows area law of entanglement, which is basically a physics-supported. So what I mean is physics support this scaling. This is not just an observation. There's a physics reason why this area law of entanglement. Yes? Okay. All right. Okay, so I'm done. Okay, so now the area law of entanglement allows me to extrapolate. But if I extrapolate, how do I know? That's the next question. How do I know if I extrapolate the QPU generates the correct answer? And this is where the complication comes. How do you know? And actually, we know because we have, as I said, we have this critical phenomena, theory of critical phenomena, and the critical phenomena, there is some scaling theory. There's some exponents that are robust. It's called universal exponents that are known. Although you cannot compute everything, you cannot compute all the averages, but these exponents you can compute independently. So if we show that these exponents are generated in accordance to quantum mechanics, at least we know that this does something quantum mechanically. And this is what we do. So I don't want to go to details. These are critical exponents that we calculate the symbols or outcome of the QPU. And these boxes are literature values. So we did not generate them. We went to the literature and see experts in the world calculated this, what numbers they give. Sometimes two papers give the two different values. We put a box which covers the two values. And you see that for all cases, so 2D, 3D, which is cubic and diamond lattice, and for biclique, and even 1D, we also added 1D, although we published 1D with Nishimori-san and others 2 years ago. But we included 1D as well, and we see that this machine generates for all problems the critical exponent in very well agreement with the result. So with that, I can go to my final plot. So now I'm allowed to extrapolate to larger problems. So this is the result of extrapolation. This is the classical GPU per second calculated based on this chi-q, how much chi-q scales, and you can use that to estimate these. So, and this as a function of a number of qubits. This dashed line is the border between the area that we could simulate and generate the ground truth, and everything is known, to some area that's just extrapolation, and we don't know the exact results. If you just follow the extrapolations, you see that you hit very large times. And I want to show two indicators. This blue line is 1 million year if we use frontier supercomputer, all GPUs of frontier supercomputer. We assume that all of them can be run in parallel, and we assume there's no memory limitation. You still have 1 million year to reach this point. And this is the global energy consumption. So the energy that you require to do this is humongous. What we mean by this is basically impossible to do classically, but just showing some how large these numbers are. And with that, I can go to my conclusion. This is the first demonstration of quantum supremacy in a problem that is interesting. That's not random number generation. The problem that matters, there are some applications of annealing, optimization, machine learning, quantum simulation. And I show you that because this is critical phenomena, our QPU follows the quantum mechanics to the largest size that we simulate. And because of area law entanglement, classical resources grow exponentially and prohibits classical methods to simulate to the level of error that the QPU generates. And with that, I thank you for your attention.
Thank you very much for the nice presentation. So now it's time for questions. We have time for 1 or 2 questions. Anybody?
Hi, thank you for the nice presentation. I would like to ask you to show again the definition of the error for the correlations.
Yeah.
Oh, okay.
Oh, sorry. Yeah.
Okay, because when you talked about the limitations of the PEPs for simulating to larger times, you showed how with bond dimension you cannot reach the limit of the QPU.
Yeah.
But why was, I think it was slide 39, why it was so constant, this error? Like in the QPU, you don't have decaying error also with not related to correlation, but that should taken into account.
Yeah, the QPU, so the x-axis is time. The x-axis was bond dimension, actually, sorry. Let me show you the plot that you mentioned.
Yes.
Yeah, so the x-axis is bond dimension. This is the QPU error as a function of time. It goes a little bit down and goes up again. So probably here you start seeing decoherence because the time goes up. So the error of QPU is almost small, the same as a function of time. But the error of PEPs grows significantly. And the reason it grows is because the neighborhood grows. And in order to keep the error, you have to increase the bond dimension. So if this error is at bond dimension, I don't know, 5, the same error now it's 12. See, even now, okay, 8 becomes 12. So for PEPs and any numerical simulation, you have to increase the number of parameters you need. But the problem is, in this case, it doesn't help you anymore. And the reason is becomes so large that it is not just the wave function, it is the way you update the wave function and solve Schrodinger dynamics is not working anymore.
I see. But why is the error keeping constant in time for the QPU? Like when you have 2 nanoseconds, 7, 20, it's almost the same.
Yeah, because the QPU is coherent, the error is due to probably some miscalibration or something, which is the same as a function of time. If you continue, so 20 nanoseconds, if you continue this probably minimum and it goes up. So
Okay.
when you go beyond 20 nanoseconds, decoherence starts hitting you and it goes up.
Okay,
So,
okay.
yeah,
Thanks.
you're welcome.
Thank you. Another question over there.
Thank you for the nice talk. Maybe just a quick question. So in the beginning of your slides, you showed the scaling agreement between the theory and experiment. Then the D-wave results kind of
Yeah, very good question.
deviated. Do you have an explanation?
Yeah. Yeah, so this is actually related to the other question. So this is time. And up to this point, it is coherent. There is the effect of environment is minimal. At this time, the environment starts kicking in and increase the energy. So this is the energy. So this difference between this coherent line and this is the amount that environment increases the energy. And yeah, becomes basically thermally excited. The system becomes thermally excited.
Thank you.
Thank you. So for the sake of time, we are going to leave the other questions for the coffee break. Let's thank again Mohammad Amin. Thank you very much. And now we have another invited talk. We have Helmut Katzgraber, Global Practice Lead of Amazon